Yes, students, this class we start, the last class we have to discuss about the cyclic group. Now we have to start the permutation group. So, it is very important and interesting topic of permutation group. Let us begin with the exploration of permutation groups by defining the permutation. We have to start with the defining the permutation. So, a permutation of a non-empty set X is a function from function pi from X to X, and that is 1 1 and on to. So, it means bijection. So, a permutation of a non-empty set S, if a function pi from X to X is bijective. So, means in the simple language we can say that a permutation of a set is a rearrangement of elements of the sets, and then we have to denoting the permutation of x by this as x. So, in general we have to denoting the permutation of this. So, simply we say that permutation is nothing but is equal to a map defined from a, we have a non-empty set S, x is there, from this x to x there is a function pi, and this function pi is 1 1 and on to, then we can say that that is a permutation. For example, we have to simply let x be a non-empty set, and then phi we have a pi is defined by pi x is equal to x. For all x is the element of it. Then this is a identity function, and you know that identity function is always bijective, that is 1 1 and on to. We have trivially proved that pi of x is equal to, you have a x. So, we have to take a pi of x is equal to pi of y, then we have to show that x is equal to y. So, clearly this is 1 1, and also there is a some every x there is, every y belongs to r, there is some x belongs to r. So, y is equal to x. So, pi of y is equal to pi of x. So, this is clearly phi of x is equal to, we can say that is equal to y. So, clearly this identity function is always, you know, that is a 1 1 and on to. So, bijection. So, this is pi map defined x to x, pi x is equal to x is a permutation, and that is a special permutation we have to say that, and this is called this is a identity permutation, and in general denoted by id suffix x or e or 1, sometimes this is we using into the form of a this form is there. So, if this map is clearly identity for permutation, we have a identity functions from the set non-empty set x to x is clearly is called is the identity permutation. Let us begin some non-trivial examples. We take a x is equal to the 3 elements a, b, c, and then pi from x to x we define in such a way pi of a is equal to b, pi of b is equal to a, pi of c is equal to c. So, we have to like this, we have a take a, this is the element of x to x, and we have to define, we have a, b and c, and then we have again a, b and c. Then we say the pi of this is map is we have to taking as a pi, then pi of a is equal to, you have to b, then pi of b is equal to, you have to say that is equal to a, and phi of c is equal to c. Then you see clearly this is every element of this is an image, and every element is a pre-image is there. Clearly by the this figure you can easily say that is defined pi from x to x defined in such a way is clearly is a 1 1 and on to. So, this is clearly is a as the non-empty set x is equal to a b c. This map in defined in such a way is clearly pi is 1 1 and on to. So, this is clearly we can say that pi is a permutation. So, this is clearly means we simply say that permutations means we have to define a map which is bijective from x to itself. Let us try some others. For consider R, the set of real numbers pi from R to R defined by pi x is equal to 3x plus y for all. Now, we have to easily show that this is 1 1 and on to, because we say that if we have a 1 1 we can say that pi of x is equal to, we have to pi of y, then clearly this is equal to 3x plus 5 is equal to, you have a 3x plus 3y plus 5, then ultimately we have to getting 3x is equal to y, 3y, and then we have a x is equal to y clearly. So, this means we can say that clearly pi is 1 1. So, this means we can say pi is 1 to 1. Now, we have to show that this is equal to some because for every x, so for y is the element of a r, then y can be written in the form of 3x plus 5. So, we can say that x can be written in the form of this is equal to y minus 5 by 3, and this is also is some real number. Then we have to say that pi of x is equal to, we have so just 3 times of a y minus 5 by 3 plus 5, and this is equal to y. So, for every y belongs to this, mean we have to x is equal to this image. So, this means clearly this we can say that this pi is onto. So, we can show that pi is 1 1 and onto. So, this is map is defined from 3x plus y is clearly is a bijective map, and then if it is bijective, then clearly we say that this pi is a permutation of R. Now, we define some another. Suppose we map take a theta from R to R again. This is again a real number to real number, and theta x we define x cube, and then again you can clearly show that again this x cube is equal to y cube is equal to x is equal to y. So, this is 1 1 and onto. So, this is theta is also is a permutation of the set of a real number. So, we can simply say that this is the there is a 3 different examples we have to taking this for as a permutation. So, now we have to move to the permutation group. So, a group G equipped with binary operation is called as a permutation group on a non-empty set X if the elements of a G are permutation of a X and the operation is star is a composition of a 2 functions. Because permutation is a function. So, we take composition binary operation as a composition of a 2 functions, and a non-empty set X if the element of a G are permutation of a X under the binary operation is composition of a 2 function. So, G equipped with a composition of a 2 function is called is a permutation. If a permutation equipped to satisfy all the properties of a group, if it is satisfied G is a set of all permutations, then we have to say that if a bijective functions. So, this is satisfy all the properties of a group, then we can say that this is a permutation group binary operation under the permutation of a function. Although groups of a permutation of any non-empty set X of objects exist, we will focus on the case where X is finite. Furthermore, it is customary as well as convenient to X to be a set of the form is X is equal to 1 to up to n, where n is strictly greater than 1. So, we have to take it clearly greater than or equal to 1. So, X we have to just take as a finite. So, let pi be the permutation on S. So, if pi is a permutation of S, then we can write in the form of a set is this form 1 comma pi 1, 2 comma pi 2, n comma pi n in this form. That means 1. So, we have a clearly is a pi from x to x. In this case, we have to taking the pi from we have to set 1 to up to n, to we have to take a 1 to up to n. Then we have the elements of this is in the form of this pi can be written into this form. Recall that the function of f from a to a is a subset of a cross a. It is sometimes convenient to describe a permutation by means of the following notation. That is pi is equal to written in the form of a 1 2 up to n, then image of a this is a pi 1, and this image of a this is equal to pi 2, and image pi 3, and then on so on this thing. So, it is better that we have to write in the form of a in this form pi can be written in this form. So, this is suppose we have to write into this form, and this is called very convenient way we have to representing into the form. So, this notation we have to write as the two row notation is called as a two row notation, or we can say that this notation is due to Cauchy and is called as a two row notation. The upper row will list all the elements of a x, and the lower row under each element I belongs to x we write image of a element of a pi I. So, clearly this is the first row, we write all the element of the set. Then in the second row, 1 under whatever the image of this is pi 1, second is image under pi 2, third one is image under the pi 3 pi. So, this means we can say that we write image of the elements second row, the lower second row under each element of a I belongs to x, we write the image of this element to this form. For example, we have to taking the n is equal to 4 and pi be a permutation 1, 2, 3, 4, and we have to define as a pi 1 is equal to 2, pi 2 is equal to, so we take as simply as take a by this we have a 1, 2, 3, 4, and then we have again we have a 1, 2, 3, 4, and that we have a map is equal to we have a pi, and we have defined pi 1, 2, we have to sorry, just a minute, I just said it like this. So, we take this is equal to you have a pi, and then we have a pi of 1 is equal to 2, and pi of 2 is equal to you have a 3. So, we have a pi of 1 is equal to this. Similarly, we have to write into this one. So, now using the two row notation is equal to we have to first row is equal to we have to write is a 1 2 3, then we have a pi of 1 is equal to when is going to 2. So, we can say that simply is equal to this is equal to in this form we have a is a pi and then is equal to 1, 1, 2, 3, 4, then 1 goes to 2, and then we have a 2, 3, 4, 2 is equal to 3, and we have a 3 is equal to 1, and 4 is equal to 4. And this is clearly you see this is the 1 1 and on 2. So, if it is 1 1 and on 2, so we just by the notation we can write as a pi of this is matlab means is you have a pi of 1, this is you have a pi of 2, this is pi 3, and then image of a pi of 4. So, this is defined by in this way. So, we can simply say that pi of can be written into a this two row notation is there. So, as we shall see, the two row notations of a permutations is quite convenient while doing the computation such as determining the composition of a two functions. Composition of permutation expressed in array notation is carried out from right to left by going from top to bottom, and then again from top to bottom. For example, I take a n is equal to 5 and pi and theta be two permutations x want to define in such a way we have to pi is defined with this is equal to means is a pi is defined in such a way pi of 1 is equal to you have a 2, pi of 2 is equal to 4, pi of 3 is equal to 3, pi of 4 is equal to 5, and pi of 5 is equal to 1. So, we have to pi is equal to we have to write, and then we have to theta, and then similarly we have to write a theta 1 5, theta 2 4, theta 3 is equal to 1, theta 2 4 is equal to 2, and theta 3 is equal to we have a 5. Now, we have to calculating the theta pi or pi theta, and then we have to just take a let us compute the theta composition pi. So, theta composition pi, now the definition of a composition of a function theta composition phi over I, then theta of a pi I, and then we have to calculating this form. So, clearly you have to theta of pi 1, so theta times theta times of a pi 1 is equal to 2, and theta 2 is equal to you have a 4. You have to just see into this form you have a clearly you have a pi of we have to pi of 1 is equal to 2, and then we have a pi of 2 is equal to 4, pi of 3 is equal to 3, pi of 4 is equal to you have a 5, and pi of 5 is equal to 1. Similarly, we have a theta of 1 is equal to 5, theta of 2 is equal to 4, theta of 3 is equal to, we have a 1, and theta of 4 is equal to 2, and theta of 5 is equal to 3. So, we have to calculating like this. So, we have a theta composition pi of 1 for example. So, we can write by the definition of a composition function. This can be written in the form of theta of pi of 1, then theta of pi of 1 is equal to, you have a 2, and then theta of 2 is equal to 4. So, this is equal to 4. Similarly, we calculate the theta composition pi over 2, this is theta times pi of 2. So, theta times pi of 2 is equal to, you have a 4, theta 4 is equal to, you have a 2. Similarly, for other we have to just take into a similar fashion is this. So, theta 1 is equal to 2, theta pi 3 is equal to, we have to this is equal to theta 2 is equal to 4, and theta 2 is equal to, we have a theta 4 is equal to 2, and then similarly this is equal to 1 and this is equal to 4 are there. So, 5 is equal to this. This means we can say that this can be written in the form of theta composition we have a pi is equal to 1, 2, 3, 4 and 5. Theta 1 is equal to, you have a 4, 2 is equal to 2 composition of these 2 is equal to 1 and 3 and 5. And this is the two row notation of theta composition. This is clearly we say that this is nothing but is equal to, we have a theta composition pi of these two this thing. So, this is a very simple way, is a convenient way we have to write the product of this. So, this means this I just representing into this. Now, if we have a theta and then this is a this we can write as a theta, and this is you have to write as a pi, and then you can see we have to say that the left right to we have to moving this. So, we have a 1 goes to, so we have to write this in the form of this 1, 2, 3, 4, 5, then 1 is equal to 2, then move to the 2 into 4. So, this is equal to 4 and that is equal to clearly 4. Now, we have a 2 to 3, 4 and then 4 to we have a 2. So, this is we have to write is equal 1 to 4 and then 4 to 2, this is equal to 2 is again is it 2. So, now we have a 3 to 3 and then 3 to 1 sorry 3 to 3 and 3 to 1 then is equal to 1, then again you see this satisfied into this condition. 4 to 5 and then 5 to 3, then again we have to write is equal to 3, 5 to 1 and 1 to 5, then is equal to 5, and then you check by we have to calculating here by this one the first row we can write always write in the form of a elements of a this set, and the second row represented as a element of a images. So, we have a composition, we take a theta and phi. So, we take a theta phi composition 1 is equal to 4, but this we take directly write the product from here. We just starting from the right side and then move to the top to bottom, and then we have to start again next matrix is top to bottom, and then we have to put the images. So, that is equal to 4 and then we have a 2 and then we have a 1 and 3 and then we can represent into this form. Clearly, I just mentioned into a this matrix we have to very clearly represent in this form of this product of a two permutation we have to represent this. Now, let us formally define as Sx the set of bijections from X to itself. We will then prove that this Sx is a group under the composition of a function. So, let X be the set and we define Sx be the collection of all permutation, that is Sx is equal to f from X to X, and f is a bijection. That means we have to S of X, X is any finite set, and Sx be the collection of all the bijecting function, and this Sx under the Now we have to finally we have to show that this Sx under the composition of a function satisfy all the properties of a group, and this form a group under the composition of a functions. So we have to first recall the very important theorem, which is very useful into the discussion of this permutations group. We have taken two functions f from a to b and g from b to c, and a, b, c are the three non-empty sets of this, and then if f and g both are 1 1, then the composition of g is 1 1. We can easily prove that if we have to just say that we have to prove that f composition g is a 1. So, g composition f over x is the same as a g composition f over y. Now, we have to assuming that f and g are both is 1 1. So, this means you have a f of x is equal to f of y, implies that x is equal to y, and g of x is equal to g of y. This also implies that x is equal to y. So, we just starting from this, so we can say that g of f of x is equal to g of f of y, and now by the property of this f from a to b. So, if f is a to the b, then we have a suppose f is a to b and x is the element of a, then f a is the element of a b, and similarly g is from b to c, then element of f a this is this. So, g of f of f of x that is the element of a c. So, that means we have a given this g is 1 1. So, this means g of some elements of a this is the same. So, this now using the property of a g is 1 1, then we can say that f of x is equal to f of y as g is 1 1. Now, again f is 1 1. So, we can say that x is equal to y. So, we can say that simply we can show that if f and g are both are 1 1, then composition of these two function is again is a 1 1. Next, showing that if f and g are both onto, then g composition f is also onto on c. We can simply really show that f we have to certain elements f x belongs to this, f is onto, then there is f x is equal to some y, and then what g is onto, then there is some z, g of y is equal to z. So, we can easily prove that g composition f is also onto on this c. And the third part is say that if f and g are both bijective, then g composition is f is bijective. So, this is very trivial. We can say that is a proof that f composition g is both are 1 1. We simply say that then composition is 1 1. If both are onto, then composition is onto, and trivially if about 2 is hold, then f and g are both are bijective, and then we can say that the composition of a two bijective function is again is a bijective. So, we use this theorem for proving that our Sx is a group under the composition of a function. So, because composition is a function, we have to take a permutation. Permutation means we have a all the collections is a bijective from set x to x. So, note that this theorem tells us that Sx is a close under the composition of a function. So, if we take a Sx, you just say that Sx we have to taking the Sx is the set of all function bijective function from x to x is bijective. So, if it is bijective, collection of all the bijective functions, so f is composition bijective, g is a bijective. So, if we have to just say that f and g are the elements of a 2 is Sx, then f is bijective, g is bijective, then by this c part we can say that f composition g is also bijective. If f composition g is also bijective, means this is also the element of x, and that means this Sx is a closed under the composition of a function. So, clearly the first condition of a this structure that Sx under the composition of function should be closed. That is clearly we can say that under this this is clearly is a closed. Now composition defines a binary operation on X. So, but what kind of a operation it? Why it is associative? We already verified in example. Unfortunately, it is not a commutative operation. So, let us we have to show that this means F composition G and G composition H are not the same in this case. We have to try to this thing. So, we have to start with this. We take a very simple example. Let X is equal to, we have a finite set 1 2 3 and define F and G by the following diagram. We have a F is defined in this way. F of 1 is equal to, we have a 2, F of 2 is equal to, you have a 1, F of 3 is equal to, we have a 3, G of 1 is equal to 2, G of 2 is equal to 3 and G of 3 is equal to. So, we have to define, and this is F of 1 is equal to, you have a 2, F of 2 is equal to, you have a defined is equal to 1 and F of 3 is equal to 3. This is a bijective, and clearly G of 1 you have to define as a 2 and G of 2 we have to define as a 3 and G of 3 defined again is a bijective. By the figure we can easily say that this set F is bijective, G is a bijective. Now, we have to try to how to write a composition. This is F into G, this is this, then again G composition F is by this figure, and then if G is X and then G F of composition is equal to this figure. So, this means we have to by this example we just say that satisfy this, we have to try to composition G composition F over I just over the 1, we can say that G of F of 1 and G F of 1 is equal to 2. So, G of 2 and G of 2 is equal to, you have a 3. Now, we have to calculate the F composition G over 1, then F of G of 1 and then G of 1 is equal to 2. So, F of 2 is equal to 1. So, we clearly see that this means we have to just say that this is G composition F over 1 is not equal to F composition G over 1. So, this means clearly we by this example we can say that the condition of a commutativity is not hold in this particular example. So, we can say that this just so that by the composition of a function, this these two functions are F and G are bijective. So, compositions by, if it is bijective, the composition of these two functions is again bijective. So, it is closed, and also we can show that the associativity is not a problem. By can we say easily show that for example, for this we take a another one more function is a H, and which is also bijective. We can show that F composition G composition H is the this is the same as F composition G composition H. So, composition of a function is associative, but is not commutative. We have to this is the one of the example I take F composition F composition G1 is not equal to G composition F1. Similarly, we have to calculating to the other, we have to just take this is equal to, we have a G composition F1 is equal to 2 is equal to 3, and then F composition G is equal to 1. So, we just say that these two are not equal. So, F composition G composition F and F composition G are different. If these two are different, then we can say that clearly this clearly this is not a we have to as a commutative condition is hold. So, this Sx will provide a new example of a non-commutative group. So, previously we have to just say that some other examples of a non-commutative, but this is the new type. We have to take a example of we have a composition of a functions define Sx provides a new example of a non-abelian group. So, this is the and very wide applications of a this we have to using this is clearly is a symmetry, and this is applications in the this chemistry is very important by using this rotations and reflections, and we have to how to we have to discuss in this chapter about the permutation. We have to uh, different types of a to finishing checking that Sx is a group, we need to verify the existence of a identity and inverse. So for the first one, recall that any set X has a special bijection in the beginning. We just saw that is a permutation identity is always is a permutation identity map is always is a bijective. So IDX we have to denote it is X. So namely this is identity permutations is a bijection function, and that is a bijection is belong to the Sx. So identity is always is a this identity permutation is a working as a existence of a identity of a this thing. Now we have to if find the inverse. So if for any f belongs to Sx, we have to find a some g. We have to show that we can for identity is clearly we have to first verify the identity. So we have to identity x from x to x, and that is equal to identity x is equal to x is equal to we have x. So whatever this f composition identity f of identity of x is equal to clearly is equal to fx, and then we have to go to the second one, identity of fx is equal to fx. So we for all x, so we have to any function f bijective function f take a composition of this identity functions. So we have to giving the fx. So this means this identity x of is a working as a existence of identity of this. So this idx serve as identity for xx, so under the composition of a function. Now we have to try to find what is the finally what do we know about any bijection. It has an inverse. In this sense we know that if f is a bijection, then its inverse is also bijection. So we know that the function especially f is linked to x and y, there is x into x such that fx is equal to y. Since f is onto but also f is 1 1, so x is unique. So this means we can find a fx is equal to y is unique. Therefore we can define f inverse y is equal to we have to x is there. So if we take this, we checking this f composition f inverse y. So f inverse y is you have it just is equal to x. So fx is equal to y, and then this is nothing but is equal to we have to write as a as a composition. This is y can be written as a identity of a y. So this means this f of composition this is equal to identity. Similarly f inverse f of x, f inverse f of x is equal to y, f inverse is equal to I x, then is equal to identity of x. So f inverse composition fx is equal to identity of x, f composition f inverse y is equal to identity of y, and then we can say that so inverse is really is the inverse under the composition of a function. Therefore by making all these observations we establish the this following result, that Sx form a group under the composition of a function. Means we have to show that this Sx satisfy all the properties of a group under the composition of a function, and we also show that this composition of a function is clearly is a this is a special type, this is known a non-abelian group. This is not satisfied the f composition G is not equal to the G composition F. We have to provide one example in the case when we have a x is equal to 1 to 3. So Sx form is always form a group under the composition of a function. So I think this I have to stop today lectures here with this proposition that Sx form a group under the composition of a function. So we have to next class we have to discuss this under this composition of a functions, how many elements are there in this and how what is the order of this group and some other properties of a this permutation group. Then we have to go to the symmetric group and some other types of a permutations group of this. Thank you very much for your attention.